Hi, everyone. Welcome back for lunch. I have the distinct pleasure of introducing our first speaker of the afternoon, Mr. Mike Hollinger. We welcome Mike as a guest here at UT, and we're very excited to hear his talk. I will give a short introduction. Mike is a director of product management, enterprise generative AI software at NVIDIA. In this role, he and the extended team help enterprises realize the transformative potential of generative AI, delivering solutions that enhance user experiences, drive operational efficiency, and enable innovation at scale. As an IBM alumni, he was most recently the chief architect for applied AI and solutions in IBM's sustainability software. And as an IBM distinguished engineer, he led efforts to integrate advanced AI capabilities into enterprise applications, enhancing customers' ability to address complex challenges. He's recognized as an IBM master inventor. He's contributed to IBM's innovation pipeline with over 60 patents and invention disclosures, a legacy that informs his leadership in shaping impactful AI solutions. Mike is passionate about shaping the future of AI technologies and their application to solve global challenges, positioning businesses for long-term success in a rapidly evolving digital landscape. I'm pleased to introduce Mike in a capacity that I know him as the president of the Austin AI Alliance, a nonprofit consortium based here in Austin, Texas, uniting leaders from Austin's vibrant AI ecosystem to foster collaboration and innovation. A graduate of the University of Oklahoma, Mike is a member of the Gallagher College of Engineering Advisory Board, where he champions the integration of cutting-edge technologies into academic programs at the university. Please join me in welcoming Michael Hollinger.
Thanks, Jay. Hey, so my husband, by the way, went to UT, so we have the whole house divided thing going on for us. And I was just here maybe 2 weeks ago. But happy Thursday, everybody. And it's a pleasure to connect with y'all. I hope to have a little bit of fun. I hope to help to share insights and also give you some takeaways that you can apply to projects that you can use to get started with projects, or maybe even take you over the finish line if you're working on something really cool. We're going to talk about 3 things. First, just the context of accelerated compute. Second, discuss robotics platforms and what NVIDIA calls the Isaac platform, and then foundational models through something we'll call the Cosmos World Foundational Model. So as an engineer, though, I do have a warm-up exercise, since we are after lunch. I do count from 0 as a computer engineer. I'm curious, for anyone who has done work with autonomous vehicles, or if you've ridden in one or seen one, from this video, what jumps out to you? Just tell me. What do you see here? The windshield wiper. The windshield wiper. That's interesting, yeah, right? What else? Navigation. Yeah, navigation's happening. Yeah, autonomous. Safety, yeah, there's a person that just was jogging the other way, right? What I actually find most interesting is the windshield wiper. That, to me, talks to the complexity of the integrations. This vehicle is a Waymo. These have sensors on the exterior of the vehicle. Why, since there's no camera behind the driver's seat, was the windshield wiper running? Was that for me? Was it for... Yeah. For the passenger. Yeah. So, passenger comfort? Did they bother to just not turn it off? Was it harder to turn that feature off versus everything else they integrated? Because they integrated into the car systems, obviously, right? So where in this discussion do you draw that line? Right? That's the fun part about this space and the point that we're in with technology. All of this is enabled by the extension of this accelerated compute platform. For those that know NVIDIA, I will just use this. For those that know NVIDIA, the company is more than just GPUs. There's an extension of capabilities that actually feed through an entire ecosystem an ecosystem that extends from partners that are building using those chips complex solutions to a software stack that extends up into vertical industries like autonomous vehicles. These things enable us, with NVIDIA as that middle layer, to bring that value to that entire stack and to provide the value of that accelerated compute to the world. And this extends even beyond building just chips to systems, to then a software stack around those systems, and enabling that capability through things that we're going to touch on with robotics and autonomous systems beyond that. Now, I'll draw out three things for us. There's really three types of compute in this that we're going to discuss. One is enabling things just based on AI. So training systems like NVIDIA's DGX. The second is, yes, robotics platforms. But the third is, I think, a critical one, something around Omniverse, this idea of digital twins, of simulation. And it's those three working together in concert that enable the tech that we're going to discuss here. And it's those three things that I think it's important to highlight, that when they work together in concert, they supply the capabilities that we'll be able to showcase and you all will be able to take away and leverage. Now, the Isaac robotics platform is one that I wanted to zero in on and hit for those that are actually building systems. So by show of hands here, who here is actually working on a robot platform or has worked on a project or is currently engaged in a project? Just a few, okay. Who here are AI experts or AI interested folks? Cool. I will hope to speak to both audiences here. And that's when Jay asked me about this topic, like, this is perfect because as a hardware nerd, as a software nerd, as someone who's sitting in that intersection of those things, I wanted to be able to help show how both of those together make this work. Now, AI is what's enabling that autonomy. It's enabling that autonomous vehicle that I took the ride in a few weeks ago. It's the capabilities that are bringing the support for everything that is moving to eventually move autonomously. It's enabling things like pick and place, right? That is smart and not scripted. And it's unlocking the value of different manipulators that exist. So all of these things between the robotic arms, the manipulators, the platforms themselves, all of these must be able to work together in order to help the robot move and accomplish whatever that goal might be. Now, those same three platforms, those same three ideas, that AI embodiment in the physical world, those three things start from, at the base layer, a robotic platform. That middle layer, that digital twin omniverse, enables then that higher level function through AI. These advancements are enabling things like multimodal AI. For those that understand AI systems from classical machine learning and deep learning, you probably have been working with reinforcement learning for quite some time. For those that don't, or who have tinkered with a chatbot, there's way more to AI than just chat. There's sensor data, there's structured text, there's image and video data. All of these things together enable us to make decisions, to enable us to build models, and enable us to integrate systems in a way that actually can drive these value points. So I want to show you from that bottom layer up. The Isaac platform is that platform that enables building autonomous mobile robots. These things that may be a platform, it may be an arm on some such, and really it's these different sets of computers working together. There's perception, there's grasping, there's dexterity support, and they run on an embedded system that is able to take and use the same GPU accelerated compute to run AI models in a way that is trained in the cloud, trained on-prem, and then embedded into the system itself. And of course, to build something like this, you have to have developer environment, you have to have a simulation environment. So that same platform enables support for physically based robots to be trained virtually. So all of these together help enable that broader foundational layer that we could call perception, manipulation, and the underlying running platform. Now, talking to AI for a sec, there's so many challenges that come up with building an AI system. It's rapidly evolving. I get news feeds that change on an hourly basis with the latest new models and latest new techniques and capabilities. It's a fun time to be in the space. There's all of the framework advances that happen with this. There's training systems that must be in place. And of course, we have to do this in a way that's transparent. Put together, these challenges really create a problem of where do you start, right? What data do you bring? What problem do you even start trying to solve? And you have to jungle through so many different layers to get to that outcome that sometimes people get stuck. Coupled with that AI platform, physical AI very much can unlock value from simulation. And these two things start to come together to address some of those pain points. The Omniverse platform is more than just a tool. It's enabling technologies to build simulation, and it connects to an ecosystem of partners that build out both CAD systems and physical systems that include things like Siemens or Autodesk or Adobe. Now, these digital twins we've talked through really are what are enabling us to do things like train a model. And synthetic data generation as a technique is so much in vogue for text, it applies equally for visual information as well. With simulation, I can actually do in just a few steps things like create a scene. I can do things like randomize what's happening in that scene. You can do variations for color, for lighting, right? Who here has built a visual AI model, an object detector? I saw some AI hands go up. Cool. What was, if you would share, what was the use case?
It was a simulation of basically a go-kart video game.
Cool.
Kind of like a rocket.
Nice. Yeah, it's a fun project. I think that's a competition, right? There's a Rocket League competition. Yeah. So in that kind of thing, if there's a new map that comes out, if there's new special scenes that come out, that visual model may work, it may not work, right? That's where cases like building that broad training data actually apply. Synthetic data generation helps with things like that. In addition, annotating these models is complex as well. So annotating your data sets for these types of scenarios becomes complicated. And finally, being able to output that in a way that you can use it is absolutely essential. So all these things, these 4 steps come together in this one simulation platform to enable building stuff that you can then leverage and use for cases like that. Turning to the robotic operating system itself, the underlying technology is absolutely essential that we talk through high performance, we talk through energy efficiency, we talk through the robustness and programmability of that platform. We've released around 20 plus packages in the Isaac ROS. And if you're curious about it, I've got some material at the end. You can go out and grab this. You can go Google it now if you want to go read through some more. But all of this is available, and it's all building blocks that you can then leverage and start from, as opposed from starting from a clean slate. Of course, underneath all of these things is enabling that same stack, CUDA, that visual perception AI model running inside of a GPU. Whether it's embedded or running out in the cloud, that same software stack enables us to run all of these things in a way that's very efficient. In fact, there was a new release just last week. There's a couple of things I want to call out here. There's been new updates for things like pick and place, which again, depending on what you're trying to do, will be very useful. And new workflows around SLAM, so for navigation use cases as well. I chose to highlight these because I wanted to make this as actionable as is possible. If you have questions about it, I actually have some colleagues that are here. We can chat after during one of the breaks. Looking at a couple of the features, perception is absolutely essential for a lot of these use cases. So dealing with multiple cameras, enabling support for flexibility of integrations across those, and being able to test across a very robust type of environment is something that you have to be able to address, and the same simulation, the same platform helps to apply there. Looking at the manipulator side, the workflows that you'll go through to enable something to locate and to manipulate the arm are driven by the same capabilities, and a whole suite of models are available under the covers there as well. So turning to the World Foundation models, this is, I think, what I find most exciting. Physical AI systems are very hard to build. It's easy to get something kind of working in a lab, and when it meets the real world, there's often something that kind of shows up unexpected. I like this because it brings a good challenge for us. Things like data collection become difficult. Teaching these systems require a huge amount of data. Training becomes resource intensive. To build out the models to enable things like that Waymo ride that I showed you, or the robots that are trying to walk across or deal with the different scenarios that we're showing, requires huge sample sizes and lots of different runs to fine tune and to build out those models. And of course, testing in the real world is risky, right? You've built a prototype, you may have only one. What do you want to do with it, right? Do you want to enable that to go interact with or potentially fall over, as some of these might have? Do you want to make a risk there? All these things come together to make and highlight the reason why this idea of foundation models or world foundation models is essential. So again, just a question for everybody. Who can define a foundation model for me? Yes, I saw AI experts raise their hands. Anybody? Sure.
Generalized model that can serve as the word definition, but a foundation.
Okay. So a generalized model that can work across different use cases. Cool. Anyone else? Based on sorry? Based on inferences you already well, I hope. The interesting thing, right, is that there's, I think, my definition of it is being able to, from unstructured data, unlabeled data, build that, yes, platform that's underneath multiple use cases that will enable other use cases beyond it, right? Something that can provide those intrinsic understanding of what happens in a given data set, so that I can then highlight with just a couple of examples or align a model to use a term that you might hear in large language models, to a given use case. That kind of stuff is enabled by these foundation models. The opposite example might be what you do with deep learning models, where I have to label data. I have to label examples of something, right? So if I wanted to take something like a visual data set like MS Coco, which has probably 100,000-ish images, give or take. Someone had to annotate 100,000 images for things as diverse as bananas and sandwiches and umbrellas and all the other random labels that are in there. If I show up with a label that is not one of those, anything trained off of that's not going to be able to work. I have to then do the annotations for that use case as well. Through the use of technologies like transformer network architectures, I can do things with a large corpus of data to enable the model to start to understand intrinsically what's happening in a given data set, so that it can start to understand things that are mobile or things that are fixed, or what logically is connected. And then I can start highlighting just a couple of things that matter to me, and we'll show some examples of that. So this idea of foundation models that can extend to world models. World models that will represent the real world, and from the real world predict future states. That, to me, is what we're enabling when we start talking through the confluence of robotics and AI. And that, to me, is what starts to differentiate the approaches that we've seen with classical ML or classical deep learning, and now what's possible with transformers and the era that we're in with generative AI. To train some model like this, you need huge amounts of data. You need to have petabytes. You have to curate that. You have to know how to encode it. You have to have an infrastructure that's capable of processing that information. And you need to have the tooling and infrastructure in place to then let you align it or use it for the use cases we're going to see. And those problems end up becoming what NVIDIA announced as Cosmos back in January. So this platform is really truly a platform. It's a world foundation model platform that enables enables, based on a diffusion model, support for text, images, video. And of course, it can output video as well. This is something that you might call a text-to-world model or video-to-world. The next is a regressive model or an autoregressive model. This is something that, given a certain state, can help predict what might be the next thing that's going to happen. If you've used a GPT text model, you know that what's really happening under the covers is, from context, in a given paragraph, sentence, whatever, that model is simply predicting what the next word? Paragraph? Token. Yes, token. Thank you. The 2% likelihood token of token, what the next token actually would be. Thank you for that. This is the same idea. The tokenization of this stream of information is something that you can apply to the same space, and the same kinds of tricks apply here, right? And that, I think, is what makes me excited about this space that we're in. All of the advances that we're seeing around aligning models, all the advances we're seeing around building with Gen AI also apply in different domains and in the same way. Now, of course, tokenization is what's important here, and being able to build a very efficient tokenization scheme is part of this portfolio. And finally, curating the huge amount of data that you collect is absolutely essential. In this case, we're talking about, as we shared, petabytes. And as someone who's built out storage systems and who's worked on a couple of petabyte storage cluster. At the time, that couple of petabyte storage cluster was an entire row of a lab, right? If we're talking about hundreds of petabytes, that's a massive amount of infrastructure. And of course, if I have that, I need to be able to move it around efficiently. I need to be able to process it efficiently. And that's where that NVIDIA AI platform, enabled by things like the training GPUs, enabled by things like our DGX platform, come into play. Now, one thing we didn't talk about is guardrails. The same premise of guardrails applies to this as well. And that can work both ways. That can be things like scrubbing automatically for faces from a video, preventing that from ending up in a training set. That can be for generating something, making sure we're not going to generate something that has a logo in it for whatever reason, right? So eliminating brands or eliminating not safe for work content. Now, all of this enables these use cases like building up scene variations. Now, you'll see that the same exact situations occurring in all four of these, but they're all in very drastically different environments. So if I'm building a visual AI system for that, I can actually work through what that might look like. And if I'm building one that's working through a physically accurate model, I can deal with things like the differences between a rainy situation, and, say, a snowy or icy situation for that same platform and that same robot. I took the Waymo that I opened up the video with a few weeks ago from an event, and it was the first time that it actually rained when I was in a vehicle like that. And yeah, we laugh about the wipers, but I'd sort of forgotten that I'm sitting in a very expensive robot going from A to B, and it's slick outside, and we're in rush hour traffic. And I didn't know if I should be more worried about this car or those other cars, right? These situations are what enables us to be able to do things like the autopilot level, SAE level 4, that is that type of vehicle, right? If you have any sort of driver assistance in your car, it's still requiring you to pay attention. It still requires the driver to be present. To have a situation like this where a vehicle is driving by itself, I've got to have a diverse enough data set. I have to have a diverse enough and a generalized enough model to handle all those weird situations. And you saw the runner on the road earlier in that video. That runner is just one example. What happens if someone's on a skateboard, right? Is there a skateboard in the data set? What's going to happen for that? Does that count as a pedestrian or not? What if I go by a cafe on the side of the road? Do the people sitting at a table count as pedestrians, right? Would you think to put that in your data set? These are the types of situations that this sort of simulation, these sorts of world models help us to address, and they enable us to help generate and build out. Now, peeling back the layers a little bit, there was about 20 million hours of video that went into the training data set for this system. That ends up being about 9,000 trillion tokens and a couple thousand hours of training. And it was trained on a 10,000 node cluster. And the mixture of use cases, or mixture of different scenarios are things like driving, things that are just what happens in the world, humans interacting in different ways, right? There's a very diverse data set built underneath here. And that diversity is what enables the accuracy of these models that we're going to place into platforms. And that quality of training data absolutely translates to a quality of result. So putting all this together, that idea of bringing a capable training platform, a capable sensing and automation platform, and then a place to simulate and to generate different training systems so I can iterate on the models, all come together to allow us to perceive the real world and to behave like humans. We were joking at lunch during the break that while we have robots that can drive me around, ultimately what we really want is something that can just fold the laundry, right? The simplest tasks, yeah, to fold the socks, just sorting the socks would help me a lot, right? I have a 3-year-old daughter, and I'm never again buying a multicolored pack of socks. But we joke about this, but these are the real problems. And yes, I can get a robotic arm to pick up a piece of clothing. Yes, I can eventually get it to fold a t-shirt. But can I just put it in my laundry room and say, go? The sweaters go over here on a hanger. The t-shirts go in a drawer over there. Figure it out later, right? That doesn't exist yet. That's the trajectory that we're on. And it's up to us as technologists, as innovators, to help move the ball toward that, right? There's a market for these examples, right? These are real things. We joke about it, but everyone here, when I say those words, has in their minds how much they'd be willing to pay for that service. And maybe zero, maybe a lot. I want to talk through a couple of these examples and show you, because I imagine these will be useful for people who are innovating in the space, or for those that are in the AI space interested in how this maps to the robotics side. These regressive models are, I think, very exciting because it applies the same techniques that work for time series models. Like LTSM sorts of use cases, for, say, a temperature sensor, or looking around here, there's probably an occupancy sensor somewhere in this room to help us to predict when to turn the lights off, right? Not just via timer, but based on the environment, what to do. This is tailored for physical AI use cases. And it drives a reduction in labor. It reduces the training loss when I'm training a model. And the architecture of it is such that you can get a very high quality output, and it's consistent and physics aware. There's a couple of different model variations available. I believe a 4 billion and 12 billion parameter model. And those can all predict something like 24 frames in the future from just 9 frames of the past. So depending on what you're trying to do, definitely I would say go out and take a look at these. They're available actually on Hugging Face. They're available via the code on GitHub, and they're actually licensed in such a way that you can use them for commercial use as well. And of course, you can use it for research purposes. The diffusion models are, as just for text, learning a latent space. And it's the same idea to build and enhance physically aware videos, and using that spatial and temporal data to be able to drive spatial and temporal consistency and logic in those videos. And of course, controlling via text is interesting and exciting. So there is labels that we can talk through, and I'll show you some examples of. And these are available as well via GitHub and Hugging Face. And the guardrails I want to highlight, because it's a very important topic for me and very important topic for us as a company. But the network is a dedicated network for improving safety, for filtering both inputs and blocking unsafe outputs. This guardrail model in any architecture, I would encourage you to include into your system, because it's what enables the system to work and be resilient in those environments. So let's talk about use cases for these. Yeah, video search and understanding is, I think, one that we've had as a use case as an industry for a long time. But being able to use these models to search through and index data is absolutely essential. So we've actually had partners that are using Cosmos Search to go and find needles in a haystack to find those edge case scenarios like wildlife in a situation, or emergency vehicles even that are moving through unnatural means and traffic, right? For reinforcement and AI feedback, there's this test evaluate loop that you have to go through. This we call the data flywheel. And being able to benchmark the performance of this type of model is absolutely essential. So what you're actually kind of seeing is that there's a human developer working through and benchmarking their model using the platform itself. Now, one of the dangers here is hallucination, right? And this is where that bridge to Omniverse becomes important. Being able to build a system in such a way that matches the real world physics is absolutely important, because you're going to place this thing into the real world. And the same problem that occurs with hallucination in language models can occur in these types of models as well, right? It's the same basic technology I hope we established. So the same sorts of systems need to be in place to enable that alignment and to enable that controllable output in a way that actually can match to the real world data, to the synthetic data. And together, we can bring that to simulation. And these things and policy models that live in something like that digital twin of a warehouse enable us to go through and simulate every possible outcome, right? And I can do all of that in software and work through all those different corner cases, all those different scenarios, and evolve the system itself so that when I go to the real world, we can choose the best path, we can choose the best optimized plan, or we can actually work through the best use of the energy for the model. Now, training these systems and all of the underlying technology is absolutely something that I want to highlight for you. So the Cosmos set of models is one that you can actually fine-tune yourself as well. You heard from Jay's introduction that I lead part of the portfolio for AI Enterprise software. And one of those core technologies is something that's a fine-tuning platform that we call NVIDIA NeMo. That NeMo platform can fine-tune these types of models as well, and can help you through trying to build out your specific use case, or build out the types of things that are important to your specific corner scenario. So whether that's things like trying to deal with tokenizing 1,000 hours of video, or figuring out how to actually best work through that training evaluation loop, these are all parts that we've addressed in this workflow managed through the software stack. And so by putting all this together, from that core Isaac AI platform that is hosting the robot, to the idea of being able to build off of that world foundation model, to being able to align that to the use cases that are important as whatever the innovation is you're trying to drive. This lets you start building up those really, truly customized platforms and models that are important to you. It's multimodal. It touches on those different types of data that are available. There's more than just text in the world, right? There's the ability to pull through those petabytes of information if needed, the ability to train in a very efficient way, and of course, to run inference on that platform, whether it's at the edge or in cloud or anywhere else. All these come together in a way that enable these innovations that I hope will soon take for granted as technologists and as consumers out in the world. But these are the things that are now available as tools in your toolkits. So there's some just takeaway stuff I want to leave with you. And I'll make sure that you all get the charts so you can have these references as well. There's first the Isaac platform, talking about perception, manipulation, simulation, and the lab that goes with it. those are all frameworks and tools that you can access, and there's documentation, demos, quick starts, et cetera, available. Second, in the nuts and bolts of building out models for leveraging that world foundation model that is Cosmos, for building up a fine-tuning pipeline, there are a whole suite of capabilities that include data loading utilities, tokenizers, training visual foundation models, training the regressive models, and of course there's just some how-tos that lay out all of this. You'll have all of these, and you can go take any one of them and start from there, depending on what your use cases are. Finally, NVIDIA itself has a conference that's in about 2 weeks. That will have a streaming component as well as the physical one. If you're going to be in California or you're from California, go take a look. Some of my colleagues can help have a conversation about what's happening out in Santa Clara. But you can also join into the live stream. So if any of this has been interesting or you want to see a double click into any of these topics, they're covered and more. And also we'll talk about what's happening next in the next couple of weeks in the major announcements. So with all that said, I think we have maybe 10 minutes or so for questions, if I timed it right.
We've got about, I think, one question.
Oh, one. Okay.
Yeah.
All right. So, sorry.
It's
My
okay.
bad.
No problem. We're going to open the floor for that question.
Oh, one question. I apologize.
Depends how long it is, I guess. All the pressure.
No.
One question. No one wants to ask you one question.
Sure.
Make this question.
Sorry. No, thanks for going along for the interaction, by the way. But
Okay.
thanks so much.
Going once. Let me join everyone in thanking Mike for this outstanding presentation.
Cheers.